Hi, Doc Revis here. In this video, I will discuss half-life decay made simple. Half-life is the time required for a radioactive element to reduce to half of its initial value. The time varies from element to element. In other words, on the periodic table, we have certain isotopes of elements that undergo radioactive decay. It's not always bad decay or harmful decay, but it's decay nonetheless. And that decay occurs in half-life increments. One way to consider this is if you had 12 marbles and they underwent a half-life, you would get 6, and further reduction would give you 3 for a second half-life. Then another half-life would be 1.5 marbles, and then you would have 0.75 marbles, and so on. For example, we show you some elements from the periodic table on this slide, starting with uranium and plutonium, carbon, radium, cobalt, iodine, and radon. They are all examples of elements having isotopes that undergo radioactive decay. Each has its own unique time period for undergoing that radioactive decay. Some are very long, and some are relatively short. So how do we do it? Half-life occurs in stepwise reductions. In other words, there are half-life portions, but they never reach zero. And here's what it looks like. If we draw a diagram where we have percent of the original element or percent of the original isotope or the original concentration on the left side of the graph, and on the bottom we draw time in half-life increments shown here from 1 to 5, what we discover is that if we start at the original percent of 100, the first half-life occurs at 50% and gives you 50% of its original value. As we continue, we take another half-life of the 50%. Third half-life is half of the previous. Fourth half-life, fifth half-life, and so on asymptotically. Another way to look at this is by looking at the percent reduction at each half-life. If we start with 100, at the first half-life, we have a 50% reduction. Second half-life, a 75%. Third, fourth, fifth, and so on. So let's take a look at this half-life concept using an example. Let's take 816 grams of uranium-238 and carry it through 5 half-life cycles. First, note that we would have 816 grams originally at the 100% level. At the first half-life, which is 50%, we would have 816 times 1/2 for 408. Second half-life would be 408 times half for 204. Third half-life, 204 times 1/2 for 102. Fourth half-life, 102 times a half-life for 51 grams. And the final fifth half-life would give us 25.5 grams. If we were to take a look at the formula for this, we would discover that the final concentration, or the final mass, equals to the initial concentration times 1/2 raised to the number of half-lives. For the example in this problem, we have 816 grams times 1/2 to the 5, which is 816 times 1/32 equals 25.5 grams, where F in this formula is for the final concentration, I is the initial concentration, and N equals the number of half-lives. So if we take the half-life degradation of 816 grams of uranium-238, which has coincidentally a half-life of 4.5 times 10 to the 9 years, we would discover that after 5 half-lives, we'd have 25.5 grams of uranium. So let's summarize this. If we have 816 grams of uranium from the periodic table, and we take it through one half-life, we would obtain 408 grams, which takes about 4.5 times 10 to the 9 years. And then we take it through its second, third, fourth, and fifth half-life to obtain 25.5 grams. And the math is shown here, where it's 1/2 times the concentration or the mass at each half-life. So if we start with 816 grams, our final mass is 25.5 grams after 5 half-lives. Another example is shown here for carbon, which also undergoes half-life. However, its half-life period is much shorter than that of uranium. And if we only had 234 kilograms of carbon, after 5 half-lives, we would have 7.35 kilograms. We could do likewise for iodine. If we start with 32 nanograms and we took it through 5 half-lives, we would end up with 1.0 nanograms of iodine. Note that the concentration or mass simply depends on the units of choice. There you have it, a simple way of looking at half-life decay of elements.